Truly excited to be back again and actually talk to you more about oxidative additions, looking at all these complexes right here. You're like wondering why are we actually diving into this? The reason why we're diving into these particular complexes is because we're trying to see how we can actually influence the main metal, which is either a transition metal or another metal, in actually performing oxidative addition. What do I mean oxidative addition? The purpose of oxidative addition is to be able to insert a metal into a specific, I would say, sigma bond. And this sigma bond, for the purpose of this particular video, is where an R group is actually interacting with an X group, where this particular X group is actually either one of the halides: fluoride, chloride, bromide, iodide, all these guys. And now those are actually going to be interacting with R because they need to introduce a sense of polarization due to the high electronegativity going from this particular direction to the other direction right there, and seeing how this can actually be influential not only in terms of the metal interacting or actually inserting itself into or between the sigma bonds, but also how these various environments, which are the changes in the ligands, will influence that to occur. Now let's look at the specific constants that is going all across the board from left to right with respect to the complexes. Now we notice that if you do the electron count, starting off with palladium here, we notice that first, the complexes right here, they all have ligands that are not charged when they are actually in the neutral state. So what that means in this particular case is that palladium has 10 electrons because it's not actually losing electrons in this particular case for now. So once this is happening, we're going to look at the other amount of electrons that are actually donated to palladium to form a complex. In all three, we actually notice that they all have 3 bonds attached to palladium. So as a result of that, we actually have 6 electrons donated to palladium, which is contributing to the overall number of electrons in this particular complexes, or those complexes, to be 6 electrons. So as a result of that, if you add both 10 and 6, we get 16 electrons. This is actually an indication that all these complexes here are actually active. If you're not active, that means that you have and you obey the 18 electron count that is required for a particular metal complex to be inactive. Now diving into this particular video, we're going to also look at what are the differences in these particular ligands that will actually facilitate in the number of electrons that palladium would donate to actually change its oxidation state from 0 to +2. +2 means that you're losing 2 electrons, and these 2 electrons are actually readily available in here for the oxidative addition in any of the catalytic reactions. So in this part, once you have those 2 electrons readily available, it all boils down to the ligands that are actually attached to palladium. Will the ligands actually act as electron donors, or will they act as electron acceptors, or are they electron rich or electron poor? What we notice in number 1 is that we have cyclohexanes, and these cyclohexanes, that are alkanes, that are quite known to be electron donors because they are actually electron rich. So as a result, they will actually push electrons towards palladium to make this particular lone pair to be highly available for any form of oxidative addition on a particular sigma bond right there. So as a result, this actually has the highest, I'd say, availability for the reaction to actually take place really quickly, really fast, and really effectively. Now looking at number 2, number 2 is quite different. There is a little bit of a contributing factor that inhibits a way of this particular metal from not actually donating its electrons, which are the lone pairs, to a specific, I would say, sigma bond or a particular ligand. The main contributing factor is resonance, and resonance is always a big deal in organic chemistry, and I know you guys have to come across this again, and this is because the compounds here, they are high electron redrawing groups, and thereby they actually need to accommodate more electrons, thereby causing a pool of electrons towards them. And as a result of that, this actually leads to, I would say, the movement of electrons going from here to there and to there, thereby creating a bond right here and making this to a positively charged, which is the palladium. And I'm going to erase this because the lone pair now becomes a bonding pair, and not only a bonding pair but a pi bond in this particular case. And what we have now is we have a negative charge on this particular carbon right there, which is actually the main reason why it is an electron redrawing group present right there. I'm going to have to redraw this. In this particular case, the overall charge is neutral, and in a way making 2 to be a little bit medium in terms of the oxidative addition process, because there is a little bit of inhibition of those lone pairs not being able to actually be involved in oxidative addition process. And finally, we have this number 3 here, and the huge contributing factor is inductive effect, because we have 3 fluorines attached that creates this huge pool of electrons towards this particular direction, thereby making this particular lone pair to just be so soaked in to the palladium, and thereby not making palladium to be effective in terms of performing oxidative addition coming from it into this particular sigma bond right there. So in a way, inductive effect is a huge contributing factor right there, and the delocalized lone pair with electron redrawing groups by induction kind of creates the least availability to donate to this particular metal, which is palladium. So this has the least, this one has the medium right here, which is number 2, and number 1 has the highest influence in terms of the oxidative addition process. So that's about it for this particular video. Please hit the comment down below, let me hear your thought about this. All the same, stay smart, believe in yourselves.